Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Come up too. We can do a co-introduction. Yeah. So I am pleased to announce that we have Andrei Voronkov visiting us today and tomorrow and Friday. Andrei did his PhD in 1987 on realizability and automatic program synthesis. Some highlights from his bio. He's professor of formal methods in the Department of Computer Science at the University of Manchester. He's co-editor of the Handbook of Automated Reasoning, which is the standard reference in the area of automated reasoning. His research interests include automated reasoning, semantic web, translation validation, I'm skipping around, logic in databases and inductive databases, implementations of logic, and his system Vampire, which he implemented with his students, has been the world champion in theorem proving 9 times in the 2 main divisions of a competition, including 6 titles out of 6 in the last 3 years. And Andrei is also Margus Vianis' advisor, so I'll let Margus say a few more words.
So basically, that's what I wanted to say. Andrei was my advisor. And I guess Tom already said quite a lot, so I just ask Andrei to give his presentation.
Okay, so I'm actually reusing slides, some of the slides that I used for my invited talk at the CSL Computer Science Logic Conference. And when you are speaking at a computer science logic conference, you have to explain to logicians quite a lot of things that they don't know about computer science. So I have a quite fairly standard material on the first slide. So I guess if you know quite a lot about model checking, etc., I will skip this material quite quickly, and then we'll go to the essential one. But anyhow, so this is the overview of the talk. So I will speak about model checking, and my main interest in model checking will be so-called linear integer systems. These are essentially systems in which you have integer value variables, and the language allows for linear expressions over these variables. So essentially you have addition. And then I will speak about reachability algorithms, and in particular about so-called local algorithms for checking reachability. Okay, I will explain what are the local algorithms. And then I will, since I will be dealing with linear integer systems, I will then go to some integer-specific material, which is Hilbert's basis, which gives you some nice representation of the set of all solutions of linear Diophantine equations. And then I will explain how these Hilbert's basis-based algorithms are implemented in our system called BRAIN, which means backward reachability analysis with integers. And then I will show you some experimental results to show how fast the system is compared to some other systems in the area. And then I will make a few remarks about how you can use this technique in general, not only for doing reachability analysis, but for some other very interesting things. For example, deciding Presburger arithmetic, using completely new algorithms for deciding Presburger arithmetic. And then I will make some remarks in future and about possible future work, about possible applications of this. And now I will go through the standard material, and if you feel you are falling asleep, then okay. But at the end, I will probably say something untrivial. Okay, so that, normally in model checking, you have a formal model of a concurrent system, you have a specification, and you have to check whether the system meets a specification. And normally when you try to formalize it in logic, you formalize it as you have a Kripke structure, a temporal formula, and you would like to check whether the temporal formula is valid in these Kripke structures. And well, there are all kinds of temporal logics, and I will be interested in temporal logics for infinite state systems. And for example, in temporal logics where you can speak about integers, and in such logics the temporal part is fairly standard, but the non-temporal part should include some primitives about, well, for expressing properties over integers. And for when we talk about infinite state systems, then there are several sources, possible sources of infinity. For example, one is when we have a finite parameter whose value is unknown. For example, we can describe try to specify, say, a cache coherence protocol, and you may have, say, several cache lines or whatever, and you don't know how many, but you would like to prove that your protocol is correct, safe, and for every possible value of this parameter. So every concrete instance of this system is finite, but if you want to prove it, to prove safety in general, then essentially you have a kind of infinite state system or infinite description. Then you may have unbounded data structures, and you may have time and other continued parameters, real valued parameters, etc. Okay, and as an example, I take this cache coherence protocol from Future Bus, and we've actually taken it from some other paper, so don't ask me what the cache coherence protocols are. I don't know much about them. But essentially, here is a description, okay? And maybe you can, well, here's some very simplified description of the protocol. And if you look at the colors here, you will see that, well, the description of protocol, this description is about some, say, processes or cache that can be in several possible states. For example, exclusive, shared, invalid, etc. And there are transitions like read modified that change the state of the system, so that these components of the system can change a state from, for example, shared to exclusive. Okay, and a typical condition that we can verify is a safety property that at any time at most one processor has an exclusive copy of a line. Okay, and another typical example is Petri nets, and the Petri nets can be described by using these integer systems. A very simple kind of integer system. So essentially, well, I will give a very simple formalization of Petri nets later. But in general, if you want to reason about transition systems in logic, we have to formalize the transition systems itself. And the typical formalization is you define a transition system as a tuple. So you have state variables, and the state variables can have values from some domain, and the state is essentially maps variables to the values. So in every particular state a variable has a fixed value. Okay, but the values may change when we apply transitions. Okay, and we can formalize transition as a set of pairs of states. And if you put all the transitions together, we get the transition relation of this system. And if the domain is infinite, we speak about infinite state systems. And now, when we speak about a symbolic representation of transition systems, then, for me, a symbolic representation is any kind of representation that deals with formulas. So it's not necessarily a representation using BDDs. So we use some logical language to speak about values of the variables in a particular state. And for example, one simple logic is a logic in which you can write formulas that a variable atomic formulas in this logic have the form a variable is equal to a value, okay? Which means that this is the value of the variable in the current state. And when we specify transitions, again, the standard technique is to introduce next state variables, a primed version of the variables, and when we describe a transition, we describe the transition as a formula of a current state variable, say v1, and the next state variable v1 prime. Okay. For example, this formula says that if in the current state the value of v1 is sent and the value of V2 is received, then in the next state, then the value of V1 prime will be wait, V2 prime will be wait, and the value of V3 doesn't change. And for example, when we try to represent Petri net symbolically using this language, variable is equal to a value. Okay, then the domain of values is a set of all integers, and if we take all places in the Petri net, okay, we can introduce a variable for every place, and the state is essentially is how many tokens are kept in this place in a particular state. For example, for this particular state, the formula representing the state is this one. For example, the variable P4 has the value is equal to 3, because there are 3 tokens in P4. Okay, and when we describe transitions in this form, and it is, well, pretty well known that if you have a complex system with lots of variables, then normally a transition changes only a very small subset of variables, so you don't want to write these formulas that, for example, the third variable and the fourth variable don't change. And normally, when you make a symbolic representation of a transition, you simply omit these variables. Okay, I'm doing this because I will demonstrate you the system, and in this system, if the variable doesn't change the value, you simply don't include it in the symbolic representation of the transition. So, for example, for this particular Petri net, you can see that, well, there are 3 transitions, green, yellow, and red. And, for example, the green transition takes 2 tokens out of nowhere and passes these tokens to P1 and P2. So, essentially, and the symbolic representation is simply that the value of P1 will increase by 1, and the value of P2 will increase by 1 too. And the value of P3 and P4 will not change. Okay?
So with this is just a syntactic shorthand. And with this syntactic shorthand, if you want to write that something changes arbitrarily, then you have to write, for example, P4 equals P4.
Yes, exactly.
So that
Yes.
But it's still part of the formalism. It's just the input language that doesn't have it. So you're just, what you're describing right now is just a syntactic sugar for something in the
Yes, exactly, yes.
Right.
Yes. But I mean, I will show you a demo of the system. I will show you some specifications, and these specifications, well, it's the example will contain 32 variables, but every transition will mention only some of them. So I'm trying to protect myself from questions, you know, because maybe I should show you this example. What kind of editor can we use for just open?
So that's just an ASCII file, right?
Yes.
And
Microsoft Word is fine.
No.
Or Notepad.
Notepad, the one below.
Yeah, Notepad.
Okay. Can you see it clearly? Yeah. So this is an example of, again, taken from some other paper of some protocol. You see that we have 32 variables, and with quite descriptive names like lock and unlock. We have the description of an initial state, symbolic description. It's a very concrete state. Every variable has a concrete value. And we have a notion of final state. And we have these transitions written in some form. Well, it's not exactly the language that I was showing you, but I will give this language a bit later. So, for example, if you take this transition T5, it says that, well, you can consider this arrow as simply a conjunction. And it says that if these conditions are satisfied in the current state, then, for example, inc y prime is equal to inc 1 y prime plus 1, etc. So this is the language that we use in the system. Right. Okay, so, and now I need some quite logical formalization of this infinite, yeah.
Isn't that the same thing as the guarded transition systems, like that people use?
Yeah, yes.
Is that exactly the same?
The word guarded will appear in 2 3 slides.
Sure.
Okay. Right. So now, since I would like to be able to express properties of arbitrary domains, and when I express this property, I can use some relations on these domains, for example, greater or equal, or I can use functions on these domains like plus. What I do is now I formalize these systems using a first-order structure. For example, it can be a structure of integers with operations plus and minus, 0, 1, and some relations, for example, greater or equal. And I always assume equality. And so I use formulas over some set of variables to represent sets of states, and formulas over the current state and next state variables to represent transitions. Okay. And we have quite a standard definition that a formula, we say that a formula with variables, with these current state variables, represents a state S if essentially S is exactly the set of states on which this formula is true in this particular first-order structure. Okay. So we always have a first-order structure on the background. When we write x is equal to y, it means x is equal to y. Or x is greater than y, then we mean that x is greater than y in this structure. X is greater than y over integers. Okay? And similarly, we can define a symbolic representation of transitions. Okay? And we can define then, well, one of the most important temporal properties, and the only property I will speak about now, is reachability. And we say that a state Sn is forward reachable from a state S0 if there is a sequence of states S1, Sn minus 1, so that we can actually go from Si to S plus, I plus 1 using our transition relation. So there is a sequence of transitions from S1 to S0 to S1, S1 to S2, etc. to Sn. Okay? We also say that Sn is reachable from S0 in n steps. Okay? And now we can also, well, I will be also interested in backward reachability algorithms, and I will explain you why. And when Sn is reachable in n steps from S0, I also say that S0 is backward reachable from Sn also in n steps. Okay, so the backward reachability is an inverse relation to forward reachability. And now, since we now have a logical formalization, I can consider reachability as simply a decision problem in the logical sense. And the decision problem is as follows. So we have a condition that represents the set of all initial states. We have a condition that represents a set of final states. And we have a formula that represents the transition relation. So we have three formulas. And the question is there any final state reachable from an initial state? Okay. So everything is given as formulas. Of course, if you formalize some transition systems as using these logical formulas, then very often the representation is not precise. You can abstract away some properties of your system. But I'm simply speaking in very logical terms. Okay. So for me, reachability is now this problem. Okay. And there are algorithms for symbolic reachability checking, and the idea of most of these algorithms is a build of symbolic representation of the set of reachable states. And sometimes we build an under or over approximation of this set of reachable states. Okay? And there are two main kinds of algorithms for forward reachability and backward reachability. Of course, we can try to do a combination of them, but essentially there are two main kinds of algorithms. And now, if you do a very simple logical analysis, of course we can express reachability in one state. And essentially, if we have a set of states symbolically represented by a formula C, okay, then the set of states forward reachable in one step from C can be described using this formula. Okay? And what is unpleasant in this formula is there exists V1. There is a quantifier that appears here. Okay? And if you describe reachability in two steps, we will have two quantifiers, and essentially the variables will be multiplied. Okay? And in general, in many standard logics, the reachability in general is not expressible. For example, if you take first-order logic, then reachability, in order to express reachability, you have to be able to express transitive closure. Transitive closure cannot be expressed. So, but reachability in a particular fixed number of steps can normally be expressed. Okay. Now I go to linear integer systems, and the linear integer systems, they are systems that can be represented symbolically using the structure of integers. So we can use arbitrary constant integer constants. We can use, the domain consists of integers, okay? We can use arbitrary integer constants, plus, minus, unary, minus, and we can use the comparison operators to describe relations between the values of variables, okay? And this is an example how, there is a standard technique that sometimes works, sometimes doesn't work, and it works for this future bus protocol when you have a system with an infinite parameter, with an infinite valued parameter, and what you do is you simply count the number of processes in a particular state. So if all processes are, if the processes are non-distinguishable, they don't have any IDs, then this technique normally works fine, as in this example. And in general, you can use integers to describe some properties of such systems. And for example, in the case of this future bus protocol, we want to check whether whether it is possible that two processes will have an exclusive lock on a cache line, and this can be formalized in this way, that there are at least two processes in the exclusive state. Okay, so you simply count the number of processes, and this is how you formalize this one. Okay, so you formalize transitions, and now I will use this language. You see, I'm using assignments here, and the assignment essentially means that the variable on the left-hand side is the next state variable. Okay, and now if you take, if you look at the literature on reachability, you will find out that this literature contains sometimes contains a description of a standard forward and backward reachability algorithms, and essentially these algorithms are very simple. So what you have is you initially have a set of final states. Okay, you apply transition backwards, and you get a larger, probably larger set of states. Okay, you apply it backwards again, you get a probably larger set of states. And at every step of the algorithm, you try to check whether the intersection between the backward reachable states and the initial states is non-empty. And if it is, then you essentially discover that there is a final state that can be reached from the initial state. Okay? And the forward reachability algorithms are symmetric, that you start with the initial states and you check intersection with the final states. Okay? This is a standard reachability algorithm, but it is not good enough for integers normally, and I will explain you why. And now, what is important is that in order to implement this algorithm, you actually have to check some logical formulas for satisfiability. And this is the formulas that you have to check. Okay? One formula is that, you have a formula that describes current states, and the current states, after you've made n steps, this is the set of all states reachable in backward reachable in n steps. Okay, so you have to be able to check that there is an intersection between current and the initial states. Okay, so you have to be able to check that this formula holds. Okay, and of course you can imagine more complex structures than simply integers. Then these formulas, this class of formulas, can simply be undecidable. Okay, and the second thing that of course, when there is no initial state backward reachable from a final state, you would like to terminate at some point. Okay, and one possibility to terminate is when you apply a transition backwards and you still get the same set of states. Okay, then in this case you can terminate because you cannot reach any more steps. And in order to do this, you have to be able to check this formula. Okay, entailment. Okay, so you have some formulas, say constraints that represent the set of current states, previous states, you have to be able to check entailment between them. Okay? And of course, there are other techniques to ensure termination. You can try to over-approximate the set of reachable states, but I will not speak about this now. Okay. So anyhow, so in order to implement this algorithm, you have to repeatedly check these two properties, satisfiability and entailment. If you can do it quickly, you can do backward reachability, you can do reachability analysis quickly. Okay. The rest of the algorithm is simple. Normally, application of transitions is simple. Okay, so this is the most important part as far as efficiency is concerned. Okay. Now, well, so far I was always telling you that forward and backward reachability algorithms are symmetric. The only difference is that we have final states, that you replace final states with the initial states, and reachability relation with the backward reachability relation, or you change the transition to the transition relation to its inverse. Okay. Now, but normally, when you specify a system, then normally most of your transitions have this form, that the value of a variable after the transition is a function of the value of the variables before the transition. Okay, so in general, these transitions have this form that, well, you have a precondition on the current state variables, okay, only on the current state variables, and you have formulas that the value of, say, this variable in the next state is equal to some function of the value of the variables in the current state. And I will use this notation for such transitions. And essentially, yes, what we have is a kind of guided systems. You can consider this as a guide to fire the transition. And when you fire the transition, you simply assign some values to some variables. Okay. And I call a system a guided assignment system, or simply GAS, if the transition relation is a union of a finite number of guided assignments. So all transitions, it has a finite number of transitions, and each transition is a guided assignment. So the transition relation is a finite union of such transitions. And currently, the input language of our system is this quantifier-free guided assignment systems. Yeah.
So now you've lost the arbitrary assignment, actually, right? Hmm? Now you can no longer express the arbitrary assignment. That is, that the variable undergoes it. Yes, you are right.
No, I mean, I express arbitrary assignments, but this is not an assignment when you say that a variable can change a value to anything, right? This is not an assignment.
Right, I should have said an arbitrary change of a variable.
Yeah. Right. So in a way, every transition is deterministic. Every single transition. The transition relation can be non-deterministic because several GATs can be true at the same time. Okay.
But you don't have integer inputs.
I don't have what?
Integer inputs. You can only have a finite number of finite non-determinism because of the...
Yes. Yeah. It's a very good remark, yes. But this is not the limitation of the approach. This is simply the current state of the system. Okay. I will speak about future work later. Yeah. But essentially, you can prove that you can represent a system as a guided assignment systems, well, more or less, when the transition relation is finitely branching. And of course, if you have enough functions to represent changes. Okay, and yeah. Okay, these are simple things, but of course you can immediately, it is quite easy to see that reachability checking, even for very simple, for these simple linear integer guided assignment systems, is undecidable. Okay, because you can very easily represent two counter machines using only 3 variables, and very simple GATs and very simple assignments. Okay. But there are some natural decidable classes. For example, broadcast protocols, they are guided assignment systems, and they are decidable. Okay. Now, if you look at this formulas expressing one-step reachability, then you will see that essentially the forward reachability and backward reachability is not symmetric anymore. Because the formulas used in backward reachability give you much simpler expressions. Essentially, when you when you do the backward reachability, the formula will be there exists V1, there exists Vn such that this formula is true, but there exists V1 such that V1 is equal to T, and A of V is simply equivalent to A of T. So at the end, you get a very simple formula. So for forward reachability, you still have this unpleasant quantifier. For backward reachability, you have no quantifiers. You don't have growing variables. Okay? You are dealing with the same set of variables. Of course, if you try to apply this idea to finite state systems, for example, to propositional formulas, then you will have ever-growing formulas, very huge formulas. If you try to apply this idea, and if you want to keep them in a compact form, then you will still need probably to introduce some additional variables for this. But in the case of ordinary integer-guided assignment systems, the formulas are short, so you don't get large explosion. And I will also later explain how to keep the size of these formulas small, which is one of the main ingredients of our system. Okay. And yeah. Okay, and for example, in particular, if a transition relation is described as a simple constraint, which means a guard plus an assignment, then the set of backward reachable states is a simple constraint is when the condition is simply a conjunction of atomic formulas. Okay. So anyhow, so when you apply these backward reachability formulas, normally if you have very nice class of formulas, then normally these formulas, the application of transitions backwards do not bring you outside of this class. In particular, if all the guards are conjunctions, then the backward reachability analysis only produces conjunctions. Okay. It's a very nice property. Now, I will speak about local algorithms. Okay. And local algorithms are different from the global algorithms. So the algorithm I try to describe here is global. So what is the difference between a local and global algorithms? I noticed on the web pages that Andreas Podelsky and Delzano, that they were visitors here, so you probably heard about, they have a system that exploits these local algorithms. But the idea of local algorithms, okay, is the following. Essentially, you have a transition relation which is a finite union of very simple transition relations, right? And you know that when you apply each of these single transition relations, then, and if you have a nice class of formulas, they would still give you a nice class of formulas, okay? So if you have a set of final states, what you do is, instead of applying the whole transition relation, you apply each transition separately. So if you have several transitions, you apply them separately, okay? And you get several different sets of states instead of one. So if you apply this global algorithm, you will get a union of this set. But here you keep them separately, okay? And then you make one more step, and you get an even larger set of transitions, okay? An even larger set of sets of states. And I will give you an example, maybe. For example, for this future bus example, then we have this, the set of final states is specified by this formula, that the number of processes in the exclusive state is at least 2, and I use E instead of exclusive because I want to draw a compact tree. And this is what is essentially what you do. You pick up all transitions, and you apply them backward, okay? You apply the inverses of this transition, and you get 4 new sets of formulas, okay? You know that these formulas are backward reachable from this one in one step, okay? And the next step, of course, you would like to keep things as compact as possible, and you would like to be able to terminate sometimes. So what you do, then you check if some of these formulas entail other formulas. Okay? And if they do, then you can simply remove some of these formulas from the search space. For example, here you see that there is a condition that E is greater than equal than 3. But this set of states is larger, because here we have all states in which E is greater than equal than 2. So there is no reason for us to consider this set of states. Whatever is backward reachable from this state is also backward reachable from this one. Okay? So we can forget about the blue states. Okay? Now we have only one set of states. Okay? But suppose that you do a global algorithm. If you do a global algorithm, then you will have a disjunction of these formulas. And when you have a disjunction, you will probably not notice that large parts of these disjunctions are redundant. Okay? And this is one of the main properties of local algorithms, that, well, maybe they are not so powerful. Sometimes they don't terminate when the global algorithms terminate, but you have very simple entailment checks. Okay? And moreover, you can discover that some parts of your search space are redundant with very little overhead. Okay?
Does this work for arbitrary transition relations, or do they have to have a special form to do the local algorithm?
Normally you should have, say, a nice class of formulas and a nice class of transitions, so that when you apply a transition, it doesn't bring you outside of this nice class of formulas. And in the case of guided assignment systems, okay, a nice class is a class where, essentially a nice class is when the guides are only conjunctions of atomic formulas. Okay? Then you will see that any application of a transition will still give you a conjunction of atomic formulas. So you only deal with conjunctions of atomic formulas. This is very nice. So if there is a disjunction, it is hidden here. For example, you see we have a disjunction of all these formulas, but we don't see that it is a disjunction. We are dealing with parts of this disjunction locally.
So you need to really be able to do things separate. I mean, the thing is, you do everything here point-wise.
Yes.
And in order to do that, you need, it's sort of like you're distributing it, and it distributes across conjunction, but it doesn't distribute across disjunction.
Yes.
Right?
Yes.
Right. So if you did it and there were disjunctions, then it would be unsound, or?
No, everything is still sound.
It's still sound.
Okay, it's a question of termination.
Termination. Oh, yeah.
Termination is
Okay.
important.
Yes.
Because you can give a very simple example. So a simple example is that when you have, say, an empty set of initial states, okay, and the final state is, say, x is not equal to 1, okay, and the transition is x is assigned x plus 1. So then you get x is not equal to 1, x is not equal to 2, x is not equal to 3, and these sets, they don't entail each other. X is not equal to 1 doesn't imply that x is not equal to 2, right? So the global algorithm would terminate immediately, because you would get x is not equal to 1 or x is not equal to 2. And that's it. Okay, then x is anything. But the local algorithm will not terminate. But we took all possible examples from all examples that we could get on the web, and we haven't seen any single example where a practical example where the global algorithm would terminate, but the local one not. But anyhow, yeah. You had a question? Yeah.
So if the local terminates, then the global will terminate?
Of course, yes. Yeah. Now, you do one more step in this example. There are only 3 transitions that are applicable now. And then you will find out again, you see all of these transitions have E is greater than equal than 2. So essentially, you are done here. You describe the set of all backward reachable steps. Okay. Now, if you come back here, this is essentially a local backward reachability algorithm. And in this local backward reachability algorithm, you have a set of sets of states, or set of formulas described in this set of states. And again, you have to perform some checks on formulas in this set. And you will see that, well, essentially, you have to do the same kind of checks. First is intersection, okay, checking satisfiability of a conjunction. Okay, and the second, checking the entailment. Okay? And now, if you imagine a huge tree, okay, a huge tree, okay, say you have 1 million nodes in it, okay, and it is very easy to see that the entailment is by far the most important operation, because you do intersection only when you expand the node, when you get a new node. But you do entailment between every two leaf nodes in this tree, every node that have not been deleted. Okay, so in general, you do a quadratic number of entailment checks and only a linear number of satisfiability checks. Of course, we know that for integer systems, you can do entailment checks by if you have a satisfiability checking algorithm. Essentially, if you have two systems of linear Diophantine equations and inequalities, then in order to check that one of them entails the second one, you simply add the negations from the second system to the first and check them for satisfiability. But okay. But anyhow, there are some bad news even for integer systems, is that first of all, satisfiability checking is an NP-complete problem, and entailment checking is a co-NP-complete problem. Okay, so if you can imagine, well, I will show you some statistics later, and I will show you one example where, say, in a couple of minutes, our system does 1 billion entailment checks, 1 billion in a few minutes. Okay, apparently you cannot do 1 billion co-NP-complete problems in a naive way. Okay. Anyhow, so you have to be able to check satisfiability, you have to be able to check entailment efficiently. Okay, and now back to integers. Okay. The way we tackle this problem over integers is the following. So in addition to storing the formula representing a set of states, in addition to storing a set of a conjunction of linear Diophantine equations and inequations, what we do is we also compute the basis of this system. And the basis is essentially some nice representation of the set of all solutions. And in case of integers, the basis is something a little bit tricky. So, of course, people were doing similar techniques over the reals, and over the reals you store a nice representation of polyhedra. But integers are much more tricky. Even if you have a very nice polyhedron, the set of real polyhedron, the set of integer points inside it can be quite disgusting. Okay, so, and even if you have a real polyhedra, for example, checking that finite one, checking that there is an integer point inside is also an NP-complete problem, depending on the representation. Anyhow, so this is the definition of a basis. Okay. Well, what we do first, so suppose we have a system of equations and inequations. Okay. Of course, we can simply speak about inequations, because every equation can be written as two equivalently written as a system of two inequations, but it's more convenient for me to speak about the basis in this way. Okay, and so I denote by hom of C the corresponding system of homogeneous equations. So essentially you remove these vectors E and L. Okay, so the coefficients become 0. Okay, so we have a corresponding homogeneous system. Okay, now I call a solution non-decomposable. Well, maybe I should have told you that from now on I will only speak about non-negative solutions. Okay, and I will later explain what can we do with arbitrary integers. So. Okay, so we call so suppose we have a solution. A solution is a vector of non-negative integers. I call it non-decomposable if it cannot be represented as a sum of two other solutions. Okay, and where one is a solution to the system itself, and another one is a non-zero solution to the homogeneous system. Apparently, the homogeneous system always have a solution 0. Okay. And anyhow, so a solution is non-decomposable if we cannot decompose it into a sum of a solution to the original system plus non-zero solution to the homogeneous one. Okay? And if you look at this definition, you will essentially see that every solution, it's very easy to see from the definition that every solution can be decomposed into a sum of non-decomposable solutions in some set. So non-decomposable solutions give you some representation of the set of all solutions. But more precisely, this we need two sets of non-decomposable solutions, one for the system itself, another one for the corresponding homogeneous system. So what you do is that you say that a pair of sets of vectors is a basis for the constraint if the following. First, every vector in, well, n means non-homogeneous. Every vector in the non-homogeneous is a non-decomposable solution to the original system. Every vector in H is a non-zero, non-decomposable solution to the homogeneous system. And every solution to the system can be represented as a linear combination of this form. So we have one concrete solution of the system plus any linear combination of the solutions of homogeneous systems with non-negative coefficients. Okay? And the same for the homogeneous system, that every solution to the homogeneous system is simply a non-negative linear combination of these solutions. And there you can prove that every system has a basis. The basis has, in the worst case, exponential size. Okay? And then, well, of course, you can prove that the basis is unique. Because if it is not unique, then some of the solutions must be decomposable. And yeah, so essentially you can prove that every system of linear Diophantine equations and equations has a finite basis, and this basis is unique. Okay. And now the question is how to find this basis. There are some algorithms for implementing how to find finding this basis. And I'm mostly interested in incremental algorithms. I will explain later why. And essentially, the incremental algorithm is the following one. We have a system of equations and inequations, and we build a basis to it. And then we add a new equation or inequation to this system. What we do, we reuse the previously computed basis to compute the new one. This is the incremental one. Okay? So you add equations and inequations one by one, and you modify the basis. Okay? And essentially, well, there is one part of the talk that I cannot, one part of this work that I cannot describe in detail. So we have an original algorithm for this incremental basis finding, okay? And we believe it's quite efficient one because we checked, we compared it with all other available algorithms for building the basis of homogeneous equations and inequations. And in most cases, it was by far the best one. Okay, but anyhow, so we have this incremental algorithm. Okay. Now, what can you do when you can compute the basis? Interestingly enough, well, the most important property is expressed here. That wait a minute, yeah, that a constraint checking and also the entailment checking becomes a quadratic operation. Well, essentially, satisfiability checking is a constant time. I'm sorry, because as soon as you build the basis, if the basis is non-empty, it has a solution. If it is empty, but so there is a mistake here that entailment checking is quadratic. Why? Well, it's very simple. So if we have two systems, C1 and C2, and we want to check them for the entailment, okay, and we have a basis of the first systems, all we have to do is we simply substitute vectors from the basis into the second system and compute the result. If all of them are solutions, then the first system entails the second one. But strictly speaking, we have to check that, well, we have a basis consisting of two parts, and we have to check it separately for the homogeneous and non-homogeneous part okay, that we have, that every solution here is a solution to the second system, and every vector in the the homogeneous part of the basis is a solution to the homogeneous of the second equation. But anyhow, that entailment checking becomes quadratic.
Assuming, well, all of the basis is exponential in size of the original system.
Of course not in the size of the original system. In the size of this constraint. Yeah, it's a very good remark. Yes. No chance. In the size of the original system. If this was possible, I wouldn't be staying here now. Unfortunately, P seems to be not equal to NP. Anyhow, now, so essentially what we've done, there are a few other systems that do this reachability with integers. One of the systems is ALV that solves constraints using built-in library for Presburger arithmetic. Okay, you can do the constraint entailment by Presburger arithmetic, right? And the system ALV uses the omega library for checking the satisfiability of this constraint. Then there is a system DMC by Delzano and Podelsky. They simply use a constraint. They use local algorithms, and they use a constraint satisfiability. They use a constraint logic programming system to check entailment and to check satisfiability. Okay, it's a very cheap implementation, and it works. Okay, and we also experimented with high tech, and high tech is not a system of this kind. High tech is a system for verifying hybrid systems. Okay. And it actually deals with the real numbers. But you can know that, if you are checking for unreachability, okay, then you can also try to use these systems for real numbers, because if you cannot reach a final state from the initial one going through real points, then obviously you cannot reach it going through integer points, right? So you can use them at least for one half of it, okay? And algorithms, satisfiability checking for reals is a polynomial problem, entailment checking is polynomial, okay? Real numbers are much easier than integers. Okay, so here are some comparisons. So first with the system ALV that uses this solver for Presburger arithmetic. And maybe I should speak about the benchmarks. We've taken benchmarks, all the benchmarks that we could find on the internet, and here are some of these benchmarks. Some of them come from formalizations of cache coherence protocols. These come from, Delzano used these formulas to prove, I think, some safety properties of Java programs, okay? And some of these systems have a reasonable number of variables, 13. Some have unreasonable, 44. Well, checking satisfy, yeah.
So what is the units for the memory? Is it megabytes?
Megabytes, yes. I will go to it. First, let's talk about number of variables, the simple part of the statistics. Okay. Then here we have here you can see the number of different operations applied by the brain system. So these are intersection checks or satisfiability checks. Okay. This is the entailment checks, and this is a nice example: 1 billion entailment checks. Okay. You can see why other systems do not behave well here, and here is a number of applications of transitions, okay, and here is the time. And by the way, the time is on modern computers it's about 10 times faster, because we used a Solaris machine for 2 or 3 years ago. They are not very fast, okay, so it's probably about 10 times faster now, okay, and this is the memory in megabytes, and you see that compared to ALV, on problems that ALV can solve, we are, say, in this case, we are 1,600 times faster, but this is a fairly simple problem. And on the difficult problems where we run, say, for 3 hours, ALV simply runs out of space almost immediately, okay? And we had the only computer with 1 gigabyte. But you can see that ALV is very greedy in consuming space.
What is ALV again?
It's the system that does a global reachability analysis, but it uses a omega library for Presburger arithmetic for checking entailment and intersection. Okay. So this is what happens when you use solvers for the Presburger arithmetic. Okay. And apparently the problem with ALV is exactly the one that I described, that you have a large disjunction and you cannot discover that actually large parts of this disjunction are redundant.
So Brain is using the local reasoning.
We use local reasoning and we build the
basis.
Yes, the basis.
Symbolic representation.
Yes, okay. Yes. And in some of these experiments, the basis for some systems are huge, so it's 100,000 vectors. Okay, and still it works reasonably. Probably not for this because it's only 60 megabytes in the worst case. And maybe for this. For some of them, the basis has over 100,000 vectors, some of the bases. And this is so the DMC is very nice. It only consumes 13 megabytes of memory. It never goes beyond 13. We ran it for 3 weeks on some examples. It didn't terminate after 3 weeks. And so on simple problems, the speed up is this one. On difficult problems, it simply cannot solve. We waited for 3 weeks for an answer. We could not wait anymore. And it was very surprising for us that the system was normally faster than high-tech. And we have no idea why. Probably high-tech has some implementation problems, because when you use this polyhedra for representing, when you have good representations of real polyhedra, I believe they should be much more compact than the basis. But I don't know. So here is a typical example. So high-tech consumes 500 megabytes of memory, and we consume 60. And on these examples, with 44 variables, it runs out of space. Okay, so these examples only we could solve, and they are very, very difficult. In general, 44 integer variables is very difficult. Okay, but there is an interesting part here. You see that there are algorithms marked by inv, and these are problems marked by inv. In these problems, what you do is, before doing a backward reachability analysis, you do some small forward reachability analysis, and you find some invariance. For example, you can find that the sum of two variables is constant. Okay? And then you add this invariance as preconditions. Okay? They are completely useless for forward reachability analysis, but you can use, in the backward reachability analysis, you get extra constraints. And surprisingly, well, these invariants make the job very difficult for Brain, because essentially most of these invariants simply restrict values of some variables to a finite set of integers. Okay? And if you look at the definition of Hilbert's basis, then of this basis, you will actually see that if you have a finite subspace, then this finite subspace is represented explicitly by the set of all points in it. And this is how you get a basis with 100,000 integers in it. Okay? And so on this, on these problems, other systems behave much better compared to, for example, on this problem, on this one, high-tech was 55 times faster than Brain, but still it's a simple one, 7 seconds. Okay. So the basis in its current form is not good when you have large finite subspaces. You have to do something else. Okay.
About 10 to 15 more minutes. We should
I'm finishing. Yeah.
Oh, okay. Sorry, I just wanted to give you a heads up on the time.
Sure. All right. So, well, then one interesting point is why you need incrementality is the following one. That incrementality essentially allows you to get rid of dependent constraints at no extra point, no extra cost. So what happens that when you throw in inequations one by one, okay, if you get an inequation that is a logical consequence of the other inequations, then this incremental algorithm terminates immediately because you already have a basis. Okay. If you already have a basis, checking that this basis is a basis for the new constraint, that you can simply substitute the basis into the constraint. Okay. And we checked examples where the depth of the search tree was over 100, and the average number of atomic formulas, and the precondition was 2. So when you go to the depth of 100, you can expect to have 200 systems consisting of 200 linear inequations. But the number that we've seen on the screen was mainly between, say, 7 and 12. So, which means 95% of the constraints are redundant, and you get it for free by using this incremental incremental function. So you not only get a simplified search space because you don't deal with disjunctions, but even inside a conjunction you can simplify quite a lot when you build this basis. Okay, and also we've discovered that we get a very nice and fast by using incrementality. You get a very fast decision procedure for quantify a free Presburger arithmetic. And we discovered it when, well, in our system you can simply ask, check this system, check this input for the deadlocks. And a deadlock state is a state to which you cannot apply any transition. Okay, so when you specify a deadlock, so you have transitions with preconditions, say P1, Pn. Okay, each one of them is a conjunction. Okay, so essentially the deadlock state is described by this formula, not P1 or Pn. So you have a disjunction of conjunctions. If you have a disjunction of conjunctions, you are in trouble because, say, well, in some examples on Petri nets, I think the disjunction had 50 members, and each of them had between 2 and 3 conjuncts. So if you see the size of this formula in CNF, then this is what you need for using Presburger arithmetic solver. Then the size would be 2 to the power 50. Forget about solving this. No chance. Okay? But when you have this, when you build the basis, then you can do some very nice tricks in proving this formula. Okay? Essentially, you incrementally compute the basis, and you discover that some parts of conjunction are redundant, some conjuncts are redundant, some disjuncts are redundant. And at the, well, so first when we work with deadlock, we tried to build this formula explicitly, okay? And then our system worked for 2 days on some input. We couldn't understand why, okay? And then we discovered what's the problem, and we simply use this incremental basic function, basis building function, for doing a much better algorithm for Presburger arithmetic. And instead of 2 days, we solved the problem in half a minute, okay, after this. Yeah.
So do you have to transform your formula to a DNF to solve the problem?
No. If you transform to DNF, you are dead. This is what happens when you do it, okay?
But the input formula can have arbitrary Boolean structure.
Yes, arbitrary. Well, we cannot deal with equivalences, okay? Right. But anything for which you have short negation normal form is okay, okay? Essentially, we need negation normal form. But if you don't have equivalence, you convert to negation normal form in linear time, okay? And this is another very interesting application. And then I was only speaking about non-negative integers. What can you do with integers? Well, if you have an integer, value in your system, then there are several possibilities. One is that when you can immediately prove that it is bounded from above or from below. And in this case, you can still deal with only one non-negative variable, okay? You can replace it by a non-negative integer variable. But if you have an unbounded one, you can represent as a difference of 2 non-negative integers and do the same with the basis, okay? And this is some future work that can be done. First of all, we are now trying to find a good algorithms and good description of basis for integers. And here you have some surprises. For example, not only, well, obviously, the basis is not unique anymore, but strangely enough, even the size of the basis is not unique anymore. So then we are very much interested in mixed integer and real systems. Okay. Then we are interested in quantify elimination. As you rightly noted, if you have a large non-deterministic system, then some systems are likely non-deterministic, and you cannot specify them using the gadget assignment system. But if you don't have gadget assignment systems, you need some kind of quantify elimination. And how does the quantify elimination work with the basis? Well, we have some ideas, but they are not final. there are some technical problems. In general, integers are very, very difficult, okay? Then, as I told you, the finite part of the basis is disgusting, okay, for us, because the basis explicitly contains all points. So what we do, we want to have a compact representation of this, and we believe that for many of these benchmarks, if we have a compact representation of these finite parts, we can go down maybe in terms of time by, say, 3 orders of magnitude very easily, okay? Then we want to do extension to full Presburger constraints, which means you have also divisibility statements, like x is divisible by 3. We want to extend it to fast decision procedures for full Presburger arithmetic. Sorry for a typo. I think this is quite possible as soon as you understand how to eliminate quantifiers. Okay. Then we want to do satisfiability checking modulo Presburger arithmetic, and essentially it is very much related to this thing, working better with the finite part of the basis. Then we want to do applications to equivalence checking, and equivalence checking with integers is a very applied problem. For example, Intel is extremely interested in finding a very good algorithms for equivalent checking with integers. And finally, we think that it can also be applied in program analysis, at least in simple cases where you only have, say, integer-valued variables, whatever. And so that's all. And I wanted to show you that how the system works. And I have a demo of the system. Essentially, okay, let me start it. And so I now run the system and ask to output statistic after every 1 million entailment checks. Okay, so you see, after about each second, this is, I believe, a bit slow computer, it makes 1 million entailment checks. And this is the system with 32 integer variables. Okay, and in this case, it is the final. There is a final state that is reachable from the initial one, and we actually get a trace of how to reach and by what transition. So you see, in this case, the depth of the tree was probably 19. I don't know. Difficult to check. Okay. So if the system finds a trace, then it finds that the final state is reachable from an initial one. It also gives you the concrete trace and concrete transitions. Okay. And here is the statistics for this case. Well, that's it. Sorry for overusing my time a bit.
Any questions?
Have you tried, so you compute these things exactly. Have you tried some approximate methods?
I should have put it on the slides about future work. Okay, we had lots of ideas, and unfortunately, we've hired not the right PhD student for this work, because all of these problems, we knew them. The system was implemented about 3 years ago. Okay, we knew all of these problems. We had all these ideas 3 years ago, and still nothing is done just because the student proved, unable to work. And the system was implemented by myself essentially in 3 weeks.
You never should have given Margus his diploma.
Sorry?
You should have kept Margus around.
Yeah, I think it was a mistake to put him to Microsoft.
So, your algorithm to incrementally compute the basis,
yes.
Is there a bound on each step? Is there a worst case bound for each step?
I'm not sure I've understood your question correctly, but if you are speaking about termination arguments, then the termination arguments are completely non-constructive in our case.
No. So you have set of constraints. You compute a basis. Now you want to add another constraint.
Yes.
You have an incremental algorithm to compute the basis. So is there a worst case bound for each step?
Exponential.
No.
Each step might be exponential.
The final size of the base, you can have an exponential number of vectors.
The final size.
He's asking, but say delta is the size of your change in your input formula, then what's going to be the worst case size of change in the basis?
I don't know whether it's exponential or. It depends on how you measure. For example, if you use some I think if you no.
Well, you only,
for example, if it is a number of variables, then probably it is polynomial.
But it's a linear number of incremental additions, right? You have an n formulas.
Yes.
You just add the first one, the second one, the third one, up to n. So there are n incremental steps.
Yes.
And so...
But it's quite possible that every step is polynomial, but the result is exponential.
That is possible. If you double each step.
I see.
But, it's a good question. I'd say I don't know. Actually, it is a co-author work with Tatiana Rybina, who is also my wife. And she is now trying to extract some nice upper bounds from this algorithm. And for example, it seems that one thing that we were able to prove is the following one. First of all, just from this algorithm, you can prove that I'm sorry. Yes. You have an exponential number of vectors in the basis, but the size. The size in the binary notation is polynomial, okay? And there is a result that the smallest solution, that there is a polynomially small solution to any system, from which you can prove NP completeness of the problem. It was proved by Papa Dimitriou many years ago using quite a complex technique, but you get it for free from this algorithm.
Right, that's
yeah, and moreover, from this algorithm you can also extract that all vectors in the basis are polynomially small, and this is a very nice result also. And also there was a recent paper at Leaks where people tried to provide better upper bounds on the size of the smallest solution for when you have lots of difference constraints. Okay, and we checked, so for difference constraints, the basis behaves very nicely. So you can prove that when you only have difference constraints, then all vectors in the basis, their components are at most 1. So they are all 0 or 1. And there are even some further restrictions. So independently on the number of constraints. So you can see that if you only have a small number of non-difference constraints, then the difference part essentially gives you a very small basis. And so I think we will be able to at least to reprove these results. And maybe and I'm sure we will be able to prove that also that all non-decomposable solutions are small, also for this case.
Yeah, if you look at all the cache polynomials, most of the constraints are difference constraints.
Yeah.
They seldom have any non-unit coefficients.
Yes, and this is probably why the system works so well in practice. Because 1 billion constraints for 1 billion entailment checks is difficult.
Do you know of the incremental algorithm that's used in the simplified theorem prover, which was also described in Greg Nelson's PhD thesis from 1979-80?
Incremental algorithm for what?
For the keeping the constraints. That is for computing a basis.
You mean the simplex method?
Yeah.
You're speaking about the reals, perhaps, right? If it's simplex, then it's about reals. Reals are very different. Okay.
Or rationals, but the...
Yeah, rationals, yes. Everything is polynomial and rationals. Here it's the solvability is polynomial over rationals. Okay. Constant checking, but here it's NP complete. So the point is, I told you that one of the unpleasant, properties of the traditional polyhedra representation for the reals is that if you have a real polyhedra, a finite one, that describes a set of real solutions, okay, still finding that there is an integer point in it is an NP-complete problem, okay, and there is an algorithm, I think, by Lenstra, okay, that tries to solve these problems by like cutting this polyhedra in parts and trying to see that if there is still an integer solution. And this algorithm is implemented in some commercial systems. Fortunately, we had one of these commercial systems installed in Manchester, and I asked my student to check. Okay, and strangely enough, this algorithm wasn't able to solve a system of, I think, 2 inequations with 2 variables. Okay, it was running forever. And you can build a basic basis in I don't know, 1 million time and 1 millisecond for this system. So it was very strange. But there are some applications where you deal with both reals and integers, and there are very nice results about quantify elimination by, I've got this from Belgium. Well, sometimes I get stuck with names in my memory. It's essentially the guys who are using automata to represent.
Wolper. Pierre Wolper.
Yes, Wolper. Yeah, exactly. Yes. Okay. You pronounce it in English Wolper, but it's probably Wolper. Okay, and yes, so they have the quantify elimination results, but there are no results on what is the basis, for example, for such systems. And I think this is also a nice future work.
You also mentioned that when you compute going backwards, like we get preconditions, you do something to keep the size of those formulas small. Could you say a sentence or two about that?
Well, it is the thing that I mentioned later is that when you add a new inequation, okay, and you have a basis, previously computed basis, then you check at essentially you can immediately see whether this constraint is entailed by the previous ones.
So in other words, it's the P part, the guard part that you check in that way. Is that right?
When you do several steps, these guards are accumulated.
Right.
As I said, you can have 200 inequations in 100 steps.
So it's the guards that you prune.
Yes, it's the guards that we prune, just because of
the assignments themselves could also give rise to larger formulas, or maybe they simplify when it's all in your.
But the coefficients grow. No, because the guards are constant. The coefficients can only grow linear. More, even the yes. I mean, of course, if you have coefficients with variable, if you have coefficients greater than 1, maybe. But we didn't have these examples. Yes. Of course, yes.
Last question.
On how many instances did you find that the result of the satisfiability and the engineering problem for integers was not the same as for reals? So like the system high-tech that you described abstracts the problem away to reals, solving it over reals, right?
On all these examples, well, for most of the examples in the table, okay, the result is unreachable, okay. So which means that it doesn't matter whether you use reals or integers. And there was one example in the table where high-tech could not solve it. And that was actually a solvable example where there was a solution, but we don't know why it didn't terminate. I really don't. I'm sorry, I don't know. Yeah, we made quite a few experiments with high-tech. We even got sometimes it even produced segmentation faults. It's probably the implementation was not perfect.
Okay, well, thank you very much.